Okay.
Yeah, great. Yeah. Thanks, Srikanth. Yeah.
All right. So yeah, thanks very much, KV, for the introduction, and thanks to the organizers in general for inviting me to give this talk. Been really enjoying this lecture series so far, and yeah, hope I learn much more. So I'm going to be talking today about algebraic complexity. So this is supposed to be like a gentle introduction from the computer science point of view to the kind of problems that are the topic of interest in GCT. So let me just start off very gently with the kind of a description of what the area of algebraic complexity is about, right? And so my talk is basically divided into, first I'll talk about the problems that we study, then I'm going to talk about the computational models that we use to study them and relationships between each other. And then I'll say a little bit about VP versus VNP, kind of the main motivating problem for us and behind GCT as well, one of the problems behind GCT. And then I'll conclude with some applications of that to some algorithmic questions. Okay, so that's essentially the program for the talk. And yeah, so feel free to interrupt me at any time and ask me questions. So it's supposed to be kind of gentle paced. I have some proofs in there, but we can always skip them. So there's no hard and fast rule about going through all of them. Okay, so what is algebraic complexity about? So algebraic complexity theory is about studying certain kinds of algorithms for very specific kinds of computational questions. So what kinds of computational questions are we looking at? Well, basically the computational questions come from families of multivariate polynomials. Okay, so we'll be looking at sequences of polynomials. So here I have a polynomial, multivariate polynomial n variables Pn of x1 to xn. And of course, a polynomial is a linear combination of monomials. So now given any such sequence of infinite sequence of polynomials, we have an associated computational problem. And this computational problem is just to evaluate the sequence of polynomials, right? So the input to this algorithmic question is a point A in Fn, and the desired output is the value that the nth polynomial Pn takes at this point. Okay, so just the evaluation problem for the sequence of polynomials. This is the computational problem that is defined by the sequence of polynomials. Okay, and this kind of language, so this is a fairly restrictive class of computational questions, but it already captures many interesting natural problems that we come across. Okay, so let's look at a few examples. So one extremely important problem is the determinant problem, right? So you have the determinant of the M determinant, which is the determinant of an M by M matrix, right? So this is a polynomial of degree M in M squared variables. It has this expansion, which is the standard Leibniz formula. So this is, of course, a very natural computational problem. So you're given an M by N matrix, you want to compute the determinant. This is useful for all sorts of reasons. You want to maybe solve a system of linear equations, or even maybe sometimes solve some combinatorial problems. So computing determinants comes in handy in all sorts of situations. So it's a very important computational problem. And it's, of course, defined by this infinite sequence of polynomials. Okay, so just a small caveat here. So when I say det M, I really mean the M by M determinant. So there's not a polynomial on M variables, but it's a polynomial M squared variables, right? So the sequence of polynomials is not defined for every number of variables, but only when the number of variables is a square of some other number. But this is not a big deal for me. So if my number of variables is maybe between M squared and M plus 1 whole squared, I'll just think of the determinant on that set of variables to be the determinant on the first M squared variables or something like that. Okay, so there are all sorts of ways to overcome these things. So this is not something I'll pay too much attention to. Okay. So another similarly defined polynomial, which also we've seen already in some previous talks, is the permanent. So the permanent of a matrix is the same as the determinant, same expansion, except for the signs, right? So you omit the sign terms. So these sign terms no longer exist, and then you get the permanent, right? So this is also, again, an important computational problem. It's related to combinatorial questions such as counting perfect matchings and bipartite graphs and other things. So later we might get to some of these questions. And so another extremely nice sequence of polynomials that is a good example for various things is the family of elementary symmetric polynomials. Okay, so what is that? So I have n variables x1 to xn. The elementary symmetric polynomial of degree d is the sum over all monomials, where all monomials of degree d in which every variable appears at most once, right? So I sum over all subsets of my n variables of size exactly d, the product of variables in that subset. Okay, And that gives me the elementary symmetric polynomial of degree d. So that's another nice example. And another extremely nice example is this polynomial that is called the iterated matrix multiplication polynomial. So that's rather a mouthful. So I just call it IMM. So the iterated matrix multiplication, or the IMM polynomial with parameters n and d, is essentially, it's kind of a mouthful. It's very simply defined. So suppose I have d matrices, right? The first of these is a row vector of dimension n. The last of these is a column vector of dimension n, and all the intermediate matrices are n by n matrices, right? So the product of all of these is a 1-by-1 matrix, or a scalar, and that's going to be a polynomial in the entries of these matrices, right? And whatever polynomial it is, that is the polynomial that is the IMM polynomial with these parameters n and d. Okay. Yeah, so that's the IMM polynomial. So all four of these are fairly naturally occurring families of polynomials, and they define interesting computational questions in all sorts of settings, right? So definitely you can agree that computing the determinant is useful. I've told you a little bit about the permanent, and of course, multiplying matrices, that's also extremely useful from a computational point of view. Okay, so any questions about the definition of any of these? Fairly clear?
Looks
okay.
Like, no.
Yeah. All right. So, okay. So a couple of caveats in this whole thing. From time to time, when I talk about the polynomials, I might just refer to some polynomial on n variables and say something. And throughout, you should think of this polynomial as being one element of a sequence of polynomials. So for example, I might say the determinant has circuits of some size, but really what I really mean is that for every n, the n by n determinant has circuits of so and so size. So those kinds of questions. So I will probably not make reference to the sequence, but you should assume without loss of generality that I'm talking about a sequence. So if it's not clear, please do ask me. And another kind of caveat that I will kind of make throughout this talk, and is typical standard in this area, is to assume that we work with polynomial sequences where the degrees are sort of moderately bounded. So what do I mean by that? If I look at the nth polynomial in the sequence, which depends on n variables, the degree is bounded by upper bounded by a polynomial function of n. Okay, it's upper bounded by n squared or n cubed or some fixed polynomial function of n. So why do this? Strictly speaking, it's not required, but it turns out that if you do this, the entire theory that we're talking about becomes a little bit cleaner. So it's best to see it first in this setting, and even if you're interested in other situations, maybe generalize from here. And the second is that this is actually true for many naturally occurring problems. Okay, so for instance, for all the 4 examples that I mentioned in the previous slide, this happens to be the case, and it's usually the case for most computational problems that we look at. So already dealing with this setting kind of is a very interesting setting for us to look at. Okay, so that's the setup. These are the computational problems that we are interested in. So now let's talk a little bit about the computational models that we'll be using. So what kind of, so we have these computational problems that we want to solve. How do we go about solving them? What are the models of computation we use? Okay, and the first and the most important one for us, and the most general one, is the model of an algebraic circuit. Okay, so what's an algebraic circuit? So an algebraic circuit is just, so it can be defined in a combinatorial way in this way. So it's just a directed acyclic graph, right? So you have the variables that your polynomial is defined on, maybe x1 to xn, they are arrayed along the bottom of the circuit. And above this, you have a collection of instructions or gates. Okay, so the internal vertices of this graph are labeled by product or sum. These product gates or these product vertices compute the products of the gates that sort of feed into them, and the sum vertices compute sums, or more generally linear combinations of the vertices that feed into them. Okay, so you can think of this essentially as a sequence of instructions. So the first instruction at the bottom here, so maybe you have first this instruction that tells you that you want to compute x1 times x2. So you have a product gate with the x1 and x2 feeding into it. And then you have another instruction that tells you that you want to compute x2 times x3. So you have another product gate. And then you have an instruction that tells you to compute the sum of these two things, which you've already computed, et cetera, et cetera. Okay, so an algebraic circuit is just a sequence of such instructions. Each instruction is made up of simple atomic objects, which are just sums, or more generally linear combinations, and products, which we think of as atomic operations that are efficiently computable. And more generally, and these instructions, as they get progressively more and more complicated, they sort of encode complicated polynomials in the underlying input variables. Okay, and as the computation proceeds, towards the end, you get to maybe the final few instructions, which don't lead to any other things. And some of these are labeled as output gates. So they're sort of the polynomials that are computed by an algebraic circuit. Okay, so what an algebraic circuit is just a kind of a representation of one or more polynomials. So you can have one or more output gates. So in this case, maybe you have two output gates. So it's a representation of one or more polynomials. And what it gives us is therefore a recipe for not just for constructing one or more polynomials, but also for evaluating polynomials on a given input. Because if I tell you evaluate these two polynomials on inputs A1, A2, A3, then you can just follow this recipe, multiply A1 and A2, multiply A2 and A3, take these linear combinations and so on, and compute the polynomials that you're interested in. Okay, so an algebraic circuit is a special kind of algorithm for evaluating polynomials. Okay, so I hope that's reasonably clear. But one small point I'd like to make here is that an algebraic circuit is not perhaps the most general kind of algorithm for computing a polynomial, right? So this is a special kind of algorithm because a more general kind of algorithm might compute as at an intermediate stages non-algebraic functions of its inputs. So for instance, if I want to compute the determinant of an n by n matrix, and I know that the entries of the matrices are integers in some range, then I could maybe look at the bits of the integer. Maybe they're integers given in binary notation or something. I could look at the bits of the integer and make some calculations based on those bits, and maybe that will help me compute the determinant. Okay, so a very general algorithm might be allowed to do operations of that form. But when we look at algebraic circuits, we look at algorithms that essentially preserve the algebraic structure of the problem. So they only use additions and multiplications and linear combinations more generally in order to compute the polynomials that they're interested in. So there are special kinds of algorithms for such problems. Okay. So is that clear? Any questions about that?
When you say linear combinations, are they supposed to be over integers, rationals, or do you allow complex linear combinations as well?
Right, we allow arbitrary linear, the coefficients of these things, like this -1 here, they're allowed to be arbitrary elements of the field. Okay. Thanks for that question. Yeah. Yeah, any other questions? Okay, so let me continue. So this is the basic model of computation that we're dealing with, an algebraic circuit. Okay, so whenever you have a model of computation, you also want a notion of efficiency to go along with it, right? So if you want to design fast computational procedure for various problems, so you want a notion of efficiency. And the notions, so we have two notions of efficiency when it comes to algebraic circuits, and they are the size and the depth of the circuits. Okay, both the size and the depth. So both of these are interesting. So what is the size? So the size of an algebraic circuit is just the number of edges in this graph. So it's a kind of the number of interconnections between these vertices that we see. Okay, and similarly, the depth of the circuit sort of measures the length of the longest directed path in the circuit. Okay, so those are the two notions of efficiency. So you can think of size as something like the time it takes to carry out this computation, this evaluation via this recipe, right? So if I have a multiplication gate with n things or k things feeding in, then it probably takes me k units of time in order to carry out that computation. And that's what we are measuring when we measure the number of edges. So it sort of measures the time it takes to carry out this computation. The depth is slightly more of a kind of a subtle measure. It sort of measures the amount of parallelism in the computation. So it's not very important for now, but it will probably be the focus in some of the later lectures. But having a low depth circuit corresponds to having very fast parallel algorithms for this problem. Okay, so for example, in this little example here, the size I guess is 8. So we have 8 edges in this, and the depth is 2. Okay, so these are our notions of efficiency. All right, so this is our favorite model of computation, the algebraic circuit. But there are also a couple of other models that we're interested in, which are sort of restrictions of this model, okay, which make some of the questions that we are studying a little bit easier. So the first one is an algebraic formula. So what's an algebraic formula? So it's just an algebraic circuit, but we place some sort of combinatorial restriction on this sort of underlying graph of the circuit. Okay, so the underlying graph, which is this combinatorial structure here is restricted to be a tree. So which means that there are no cycles of any form. So if I go back to the previous example, you probably see that there are some cycles here. So there are some they're not directed cycles, they're undirected cycles, but there are some sort of cycles here. In other words, is the output of a single computation can be used multiple times. Okay, a formula is an algebraic circuit where we forbid this kind of thing from happening. So the underlying graph is a directed tree. Okay, so this is what an algebraic formula looks like. So this definition sounds a little bit, may sound a little bit unnatural. So why would you restrict a circuit to have a tree-like structure? But in fact, it's extremely natural, right? Because, and the reason for that is because formulas are just algebraic expressions. So when you take your favorite polynomial and write down an algebraic expression for it on a piece of paper, what you're really doing is constructing a formula for it. Okay, so it's a good exercise to sort of convince yourself of this. So for instance, if you write down a polynomial, maybe x1 plus x5 times x3 plus x4 plus, I don't know, x7 times x9 plus x1, you should convince yourself that you can rewrite this as an algebraic formula, right? It would be something like this. So it would be something like x1 plus x5 times x3 plus, I forget what I've written here, maybe it's x1, etc., etc. So it will be something like this. And the combinatorial structure you just construct will be a tree. Okay, so it will not have any sort of cycle. So an algebraic formula is just a standard algebraic expression as you would write down on a piece of paper. Okay, and the size of the formula, the way we defined it, which is just the number of wires in this construction, is just the size of the expression. Okay, so if you write down an expression which has, I don't know, 100 symbols, you'll get a formula of size roughly 100. Okay, and whenever you write down a formula like this, of course, it gives you a recipe for evaluating the polynomial, and that's exactly what we're talking about when we're talking about algebraic formulas. Okay, so does this make sense? Any questions?
Srikanth, since all your examples of circuits are quite simple,
right?
I want to ask, you are not allowed to multiply more than 2 at the same time. So, I mean, x1, x2, x3, can I do them considered one once, or do I have to do x1, x2 and then take x3 and multiply them?
So that's an excellent question. Thank you for asking that. So as of now, I have not made any sort of restriction on how many things you can add or multiply at a given gate. You can multiply any number of things. And of course, when you multiply more than, I don't know, when you multiply k things, you take k in terms of the size of the underlying structure. So, so other than that being a constraint, there is no problem in multiplying many things or adding many things. You can define things the way you say, where you only add 2 things at a time or multiply 2 things at a time. And it's not hard to see that in terms of size, they are roughly the same because, so let me just draw a small example here. So suppose you want to add, I don't know, 4 things here. In a circuit, you could always convert this to another circuit that sort of does these additions iteratively. So maybe maybe I'm adding A, B, C, D here. So I could first add A and B and then add C and D. So I could always do this conversion. And this conversion will not cause me to lose too much in terms of size. Maybe the size would double or something like that. But it would cause me to lose quite a bit in depth. So it would blow up the depth of the underlying structure. So in general, we just allow arbitrary fan-in, and then everything works out. But if you can in general convert this to bounded fan-in, like you say, add only 2 or multiply only 2 at a time, but then the depth of the structure blows up, though the size remains roughly the same. Okay, so does that answer your question?
Yes, thank you.
Okay, thanks. Yeah, any other questions about algebraic formulas?
Sir, when we club, can we club that x2 leaves, 2 x2 leaves?
Right, so you're saying, can we do this?
Yeah, but
so in an algebraic circuit, you can. In an algebraic formula, you're not allowed to do that. So it has to be a tree.
So can you go to the previous slide?
Yeah. Yeah, sorry for that. Let me just clear these. Yeah, yeah.
Even here, I can, it seems I can break that x2 leaf into the pieces. and make
Yes.
a circuit into a expression or formula.
Right. So it's a very good thing you point out. You can here make 2 copies of this x2 and convert this into a formula by making such replications. But in general, that will increase the size of your underlying circuit / formula. So it'll increase. So converting a circuit to a formula can be done in principle, but that can result in a larger size.
Okay, so it can always be done. See, even if I convert x2 into the pieces, is it a formula or a circuit?
So just converting, breaking x2 into making 2 copies of x2 here would not yet give you a formula, because you would still have other kinds of problems up top, right? So so let me see if I can find this thing here. Oops. Yeah, so typically in a formula, the result of every computation can only be used once, whereas this computation is also used twice here. So there's not, strictly speaking, a formula yet, but making some other modifications, again, by replicating these things, you can convert this to a formula. Okay.
Okay, that makes it clear. Thank you.
Okay, great. Yeah, thanks for these questions. So now, so just going back to this algebraic formula. So a formula is just an expression, and the size of the formula is simply the size of the expression. So in particular, you can see already that every polynomial can be written as an algebraic formula, right? Because every polynomial, of course, you can always write an expression for it as just a sum of monomials. So this will give you some sort of formula for it. So every polynomial does have some sort of algebraic formula. And in fact, it's an algebraic formula of just depth 2, because it will just be a sum of product of things. So it'll just be a depth 2 formula. Okay, but in general, the size of this formula will be very big. So in general, it'll be the size of the formula will be roughly the number of monomials of degree d, so which is this binomial coefficient here. And you can check that for reasonable values of d, maybe d equals n or something, this will be exponential in n. Okay, so this is a very large number. And what we would like to do is actually come up with more efficient formula / circuits for our underlying polynomial. Okay, so that's the setup. So this sort of concludes my second model of computation. I want to tell you about one more, but before I do that, I need to talk about reductions. Okay, and this is a very important concept in theoretical computer science in general, which is very useful. So when you have 2 computational problems, so for instance, here we have 2 families of polynomials, Pn and Qm. A reduction is essentially one that allows you to use an algorithm for one of these problems in order to solve another. Okay, so it allows you to turn one of solving maybe Pn into an instance of solving Qm and use the algorithm for Qm in order to solve Pn. Okay, so how does it work? Well, in the very restrictive setting that we are looking at, we are going to talk about only very well-behaved algebraic reductions. Okay, so what are these reductions? So if you've been following some of the earlier lectures in this series, you've already seen these, but let me just go through it anyway. So these are what are called projections. Okay, so I say that the polynomial sequence Pn is a projection of the polynomial sequence Qm if every element of the first sequence can be written as some element of the second sequence, where the variables of the elements of the second sequence are replaced by linear polynomials in x1 to xn. Okay, so Pn of x1 to xn can be written as Qm for some m, a function of n, of linear functions in these x1 to xn. Okay, so I can sort of evaluate Pn by taking an algorithm for Qm and then plugging in, making these linear substitutions for the variables in the algorithm for Qm, and hence get an algorithm for Pn. Okay, so it allows me to reduce one computational problem, Pn, to another, the one defined by Qm. Okay. So this kind of notion is extremely useful. So it allows you to use sort of one recipe in order to get recipes for other recipe for one sequence of polynomials to get recipes for other sequences of polynomials. So this kind of idea is very useful. And it's not just useful from the point of view of coming up with new algorithms. It's also useful from a point of view of defining classes of new algorithms. Okay, so you can come up with, you can use any sequence of polynomials, any given computational problem, let's say Qm, and use reductions to define a new computational class of algorithms, which is the set of all. So all algorithms can be phrased as apply a reduction and then use the algorithm for Qm. Okay, so take your favorite sequence of polynomials, look at all the things that reduce to QM. They all have an algorithm of certain form, which is to apply the algorithm for QM on a collection of linear polynomials. And the set of all these things, all polynomials defined this way, gives you a kind of this gives you a class of algorithms which can be interesting or not interesting depending on the class QM of polynomials you start with. Okay, so for certain choices of QM, this is not very interesting at all. So for instance, if you just take QM to be a collection of constant polynomials, you don't get anything that's very interesting. But for certain other classes of polynomials QM, this can be a very interesting class of algorithms. Okay, and we're going to use this idea in order to define this one other class of algorithms that are called algebraic branching programs. Okay, so let me try to show this in action. Okay, so the problem that we are actually going to reduce, take projections of, is this polynomial that we saw already, which is the iterated matrix multiplication polynomial. Okay, so just to recall, so here I've made the degree parameter equal to the size of the matrix. So the IMM polynomial with parameters n and n is just the polynomial you get when you multiply n matrices. The first of which is an n by 1 or 1 by n row vector. The last of which is an n by 1 column vector, and the intermediate matrices are all n by n matrices. Okay, so this is this polynomial IMM. Okay, and so if let's just try to write this down as a sequence of monomials, right? So what would that look like? Just by sort of the laws of the rule for matrix multiplication, this is going to be the sum of all monomials that look like this, right? So every monomial which in this polynomial is going to multiply one entry of x1 with one entry of x2 with one entry of x3 and so on. And furthermore, just because this is matrix multiplication, the column index that I have in the first matrix is going to match the row index in the second matrix. The column index in the second matrix is going to match the row index in the third matrix and so on. Okay, so there's going to be a sum of monomials of this form, where the sum runs over all choices of these indices I1 through In minus 1, where I1 denotes sort of the column index of the first matrix / the row index of the second matrix, and I2 denotes the column index of the second matrix / the row index of the third matrix, etc., etc. Okay, so this is just the expansion of the iterated matrix multiplication polynomial. So now there's a kind of a nice graph theoretic way of seeing this, which will be quite useful. So another way of viewing the same polynomial via a graph is as follows. So consider the following kind of directed graph. Okay, so this directed graph has a source node, which I'll call S, and a sink node that I'll call T. And in between the source node S and the sink node T, I have n minus 1 layers of vertices, each of which has n vertices. Okay, so I have n minus 1 layers, each of which with n vertices, each of which has n vertices. Okay, and what do these n minus 1 layers represent? They essentially represent the choices for I1, I2 through In minus 1. Okay, so they represent the choices for these indices I1 through In minus 1. So for instance, the first layer, so I start from the vertex S, the first layer just after S has a n vertices, and though that sort of corresponds to the choices for I1 or the column index in the first matrix. Okay, so I have n of those, and that has, so there are n values 1 through n, and each of them corresponds to taking one of these variables, x11, x21, x31, etc., etc. Okay, and so what I do is I sort of put an edge between the source vertex S and each of these vertices, and I label each edge by the variable that that corresponding choice gives me. Okay, so if I'm picking the first entry in the first column, in the first row vector, then I sort of label that with x1, with a variable x11, and similarly x21, etc., etc. Okay, and similarly between every pair of layers here, every pair of layers, I have a kind of I have all possible edges, and each of them gives me a choice for one of these indices, and I sort of label the corresponding edge with the variable that comes about in this monomial from that choice. Okay, and when I do this, I can, in terms of this directed graph, I can define this iterated matrix multiplication polynomial in a very nice combinatorial way. And what is that? Well, the iterated matrix multiplication polynomial can simply be defined as just taking the sum over all paths from the source S to the target T, right? So when for each path, I sort of just take the products of the labels along the paths. Okay, right? And when I do this, I'm exactly summing over all of I1 through In minus 1, And as I take the products over all the labels, I'm exactly getting this particular product of variables. Okay. And so the iterated matrix multiplication polynomial can be defined in terms of a directed graph in this very neat combinatorial way. Yeah. So does this make sense? Any questions about this? Okay. So if not, so let me just say that now we're going to define algebraic branching programs, and the way algebraic branching programs are defined is via reductions or projections from this iterated matrix multiplication polynomial. So I start from this polynomial and I look at what kinds of polynomials I can do by projections from here, which means that I substitute variables to this polynomial, the input variables of this polynomial, by linear functions in some other subset of, in some other set of variables. Okay, so what's the end result of that going to be like? Well, the labels of all these edges in this combinatorial structure, they're all distinct variables. So when I project, potentially I can get a different linear function for every edge of this underlying graph, right? And so the kind of polynomial I'm going to get is I'm going to sum over all paths, and for each path I'm going to take a product of linear functions, which are the labels of these different paths. Okay, so that's the kind of thing I'm going to get. Yeah, and so this is the kind of thing that we will define an algebraic branching program. But before I do that, so just a small note here. So if I set the label of a vertex to 0, right? If I take a variable and I substitute it by the linear function, which is the 0 linear function, then the end result of that is that every path that passes through that edge, the corresponding product is going to be 0. Okay. So the end result of that is the same as essentially deleting that edge from the graph. Okay. So as I set certain linear functions to 0, I end up deleting certain edges from this graph. And by setting a collection of linear functions, let's say all the linear functions that go out of a certain vertex, as if I set all the variables, those corresponding linear functions to 0, the end result of that is to delete all outgoing edges from certain vertex. And the end result of that is to delete that vertex itself from the underlying graph, right? So as I make these substitutions, I can also view this process as transforming these variables, of course, to linear functions, but also deleting some of these vertices and some of the edges from the underlying graphs. Okay, and so this is what sort of motivates this definition of an algebraic branching program, which is exactly comes from this combinatorial definition. I start off with this directed acyclic graph. It has a source node and a target node. And you've got this layered structure, which means that the vertices are divided into layers with all edges going between one layer and the next. And each edge of this directed graph is labeled by a linear function in the set of variables that you're interested in. And now when you have a structure like this, the polynomial defined by this combinatorial structure is exactly the way the iterated matrix multiplication polynomial is defined. So you just sum over all paths going from S to T. And for each path, you take the products of the linear functions on the labeling the edges that appear on the path. Okay. And as I sum over all this, the polynomial that you get is by definition the polynomial computed by this structure, which is the algebraic branching program. Okay. So this is sort of the definition of this computational model. It's a little bit complicated, but if you imagine it as coming from an instance of iterated matrix multiplication, in my opinion, is sort of the motivation for it becomes fairly clear and straightforward. Okay. So any questions about this? Okay.
No.
Yes.
So nothing in the chat also, I think. Yeah, nothing in the chat.
All right, great. Okay, so so let me just do a couple of small examples, because this is kind of a mouthful of a definition. So let's just start with some very simple examples. So suppose I take a graph which is simply a path, right? And I have every edge of this is kind of labeled by this thing, these distinct linear functions. So this is just an algebraic branching program where there's just one path going from source to target. And so I have, this is my underlying polynomial. So it's kind of a very simple example. Slightly more complicated example is this one, right? So I have a slightly bigger graph here. So again, the polynomial represented by this algebraic branching program is I sum over all paths going from source to sink. And for each path, I take the product of the things, the labels of the edges that appear along the path, and I sum this over all paths. Okay, so I get this polynomial. And you can see this is just kind of a standard instance of iterated matrix multiplication sort of written out as an algebraic branching program. Okay. All right, so these are sort of three models of computation. So we've seen algebraic circuits, which is sort of our main, the star of the show, the main model of computation. We saw a restriction, which are algebraic formulas. And we saw something that was slightly different, algebraic branching programs, which essentially arise as projections from the iterated matrix multiplication polynomials in various ways. Okay. And for this last model, I forgot, I also need to define the notion of efficiency, right? So whenever we have a computation model, we should have a notion of efficiency. So what's the notion of efficiency here? Well, if you have an algebraic branching program, right? Yeah. So we define its efficiency to simply be its size, which is just the number of vertices in this underlying graph. Okay. So just look at all the layers, sum up the number of vertices in each layer, and that's the size of the algebraic branching program, and that's our notion of efficiency. Okay. Just a small observation here that if you're getting an algebraic branching program like this, you can imagine this as coming from, so let's say you have an algebraic branching program of size S, right? That means there are at most S vertices in each of these layers. So you can imagine the structure as coming from a projection of IMM where you have S vertices in each layer, right? Because you have at most S vertices in each layer here, but you can imagine that you started off with S vertices in each layer there. You start off in a bigger graph where you have S vertices in each layer, and now you made some substitutions, send something to 0, substitute other things by linear functions, etc., and obtain the structure of this form. Okay, so every algebraic branching program of size at most S essentially comes about as a projection of an instance of the iterated matrix multiplication polynomial with parameters S and S, which is multiplying S many S by S matrices. Okay. So this is a kind of a nice observation. All right, so we have three models of computation that we've defined. We have circuits, formulas, and algebraic branching programs. And so now let's look at a little bit about how they define certain complexity classes and how these complexity classes relate to each other. Okay, so suppose now I have a computational problem. Right, and a computational problem for us is just a sequence of polynomials. Now I'm interested in understanding the complexity of this problem in each of the models that we've defined. Okay, so for instance, so I see that there's a raised hand somewhere. So
yeah, I have a quick question.
Yes.
Can a circuit be expressed as an algebraic branching program?
Okay, can a circuit be expressed as an algebraic branching program? So it's a great question. So every circuit can be expressed as both a formula and an algebraic branching program. But the real question is, what is the size, right? So if you start with a circuit of a certain size, you might be able to express it as an algebraic branching program of a different size. But the question is, how much bigger is the algebraic branching program than the circuit? Okay. So in principle, all these models of computation that we're talking about, they're all universal in the sense that they can compute any polynomial that you want. But really, it's the notion of efficiency that we are interested in now. So yeah, you can convert a circuit into an algebraic branching program, but as far as we know, that involves a certain blow up in size. And yeah, it's an interesting question as to what is the size blow up required.
Okay, thanks.
Yeah. Okay. All right, so great. So we have a computational problem, Pn, defined. And what we're interested in is in each of these models of computation, trying to figure out the most efficient algorithm for evaluating Pn. Okay, so when I talk about the circuit size of Pn, this is the smallest size of a circuit for this polynomial Pn. And similarly, I can talk about formula size, which is the size of the smallest formula, and ABP size, which is the size of the smallest algebraic branching program representing the polynomial Pn. Okay, and each of these is of course a function of n, right? Pn is an infinite sequence of polynomials, so each of these is a function of n. And I'll say that Pn has polynomial size circuits if the circuit size of Pn as a function of n is upper bounded by a polynomial in n. Yeah, so it's upper bounded maybe by n squared or some n to the c for some fixed c. Okay, and similarly, I can say that the formula size of Pn is upper bounded by a polynomial in n, so it has polynomial size formulas, or it has polynomial sized ABPs, and so on. Okay. And so you can see that the notation here is a little bit messy. I have my computational problem is defined by polynomials, and then I'm talking about polynomial size. So sometimes I might just say efficient circuits. And when I say efficient circuits, you should take it to mean polynomial sized. Okay. So efficient circuits, efficient formulas, efficient ABPs, etc., all refer for now to polynomial sized. Okay. And so this is really kind of the gold standard that we are for now aiming for. Okay, so when we have a sequence of polynomials, we would like to know whether we have an efficient algorithm for this computational problem, either in terms of circuits or formulas or ABPs, which is to say, does it have a polynomial sized family of circuits, polynomial sized family of formulas, polynomial sized family of ABPs. Okay. And depending on whether this happens or not, we say that this polynomial lies or does not lie in some class that we give various names to. Okay, so for instance, in the setting of formulas, we look at polynomial families that have efficient formulas, and this class of computational problems that have efficient formulas, we give it a name that we call VF. Okay, and similarly, we can define complexity classes corresponding to having efficient algebraic branching programs and efficient circuits. Okay, so these are kind of the main objects of study in algebraic complexity theory. We have these computational problems defined by polynomials, and we have interesting complexity classes which are defined by, in our case, 3 different models of computation. And our aim is to figure out when a certain interesting computational problem or a naturally occurring computational problem lies or doesn't lie in one of these complexity classes. Okay. So is this
sorry, was
yes.
there a raised hand again, or did I? No, sorry, I thought I had seen.
Sir, can you go to the previous slide?
Yes, of course. Yeah. Yes.
See, is that ABP problem is for a polynomial or for a sequence of polynomials?
Right. So all of these things are for sequences of polynomials. Right. So when I have a sequence of polynomials, for the nth polynomial, I can talk about the smallest ABP for that polynomial, and there's going to be a smallest ABP for each n. And now the question is, how does this, as a function of n, the size of this ABP vary as a function of n? And what we would like is that this is bounded by a polynomial function of n.
Okay. Okay.
Yeah,
thank you.
Yeah, so maybe once Srikanth, I can just repeat that determinant, for example, runs over all n, so that then it gets fixed, perhaps. No?
Right. So yeah, so kind of a running example to kind of keep in mind is maybe something like the determinant, right? So if you have the square root n by square root n determinant, which is defined on n variables, then you can talk about what is the smallest circuit for the square root n by square root n determinant. And we would like, and we will, in fact, it is true that the smallest circuit for a square root n by square root n determinant is of a size that is polynomial in n. So it's an efficient circuit. Okay, and this is kind of what we want. So we want to be able to come up with, for the problems that we're interested in, efficient algorithms. And for now, efficient means polynomial in the number of underlying variables. Okay. All right, great. So this was quite a bit of theory. So let's do maybe a couple of examples. Okay. So I want to talk a little bit about this polynomial family, the elementary symmetric polynomials, and sort of maybe play around with it a little bit and talk about circuits, algebraic branching programs, etc. for this family. Okay. So it turns out that this family has polynomial sized circuits, algebraic branching programs, as well as formulas. So it's sort of in all 3 of these complexity classes that we saw on the slide. Okay, but let's just kind of prove this a little bit formally, and maybe it will help concretize some of the definitions we've seen. Okay, so let's start out by constructing a family of circuits for this sequence of polynomials, right? And just to be clear, when I talk about the dth elementary symmetric polynomial, the degree d elementary symmetric polynomial, I'll think of d as some function of n. Yeah, and a good example to keep in mind is maybe d is n by 2 or something. Okay, so just think of d as n by 2. And we're looking at the n by 2 degree elementary symmetric polynomial. Okay, so how do we construct circuits for this? So let me start off with a very simple identity that you can convince yourself of, right? So now the d degree elementary symmetric polynomial is the sum over all d subsets of the variables, right? And now this d size subset can either contain xn or not, right? And if I split the terms of the elementary symmetric polynomial based on whether they contain xn or not, I get this recurrence. Okay, so I get that the degree elementary symmetric polynomial is xn times ed minus 1 plus ed in n minus 1 variables. Okay, and this kind of gives me an idea for computing or evaluating this polynomial, which is to kind of do it inductively based on n. Okay, so suppose I've already evaluated this polynomial on n-1 variables. This kind of gives me a recipe to evaluate it on with n variables. But the only thing is that this recipe also requires me to evaluate not just the degree d elementary symmetric polynomials, but also the degree d-1 elementary symmetric polynomial. Okay, so in order to use this recurrence to evaluate E and D, what I'm actually going to do is not just evaluate E and D, but evaluate all elementary symmetric polynomials of degree up to D. Okay, so not just degree D, but degree 0, degree 1, all the way up to D. Okay, and that's going to be my idea of my circuit. So we'll construct circuits not just for E and D, but circuits that evaluate each of E and 0 to E and D individually. And what we'll do is we'll start with n equals 0 and we'll build all the way up till n. Okay, so let's see how to do this. So once I tell you this idea, it's actually quite easy to do it by yourself, but let me just do it here anyway. So what this circuit will do is that it will have gates that do each of these computations. So let's start off at the bottom of the circuit. So at the bottom, what we are doing is we are computing the elementary symmetric polynomials of degree 0, 1, all the way up to D, but in 0 variables. Okay, in 0 variables. And you can check for yourselves that by definition, these are just constants, right? So the elementary symmetric polynomial degree 0, actually that we define to be 1 in 0 variables, but all the others are just 0. Okay, and now in the layer above that, what we are going to do now is to compute the elementary symmetric polynomials of degree up to D, but now in 1 variable. Okay, and how are we going to do that? Well, we are just going to use this recurrence on the top of the slide. So we're just going to say, oh, E1D is x1 times E0D-1 plus E01, yeah, or E0D. And we're going to use this recurrence in order to compute each of the elementary symmetric polynomials of degree up to D in 1 variable. Okay, and then similarly, we're going to use the recurrence again to compute each of the elementary symmetric polynomials in 2 variables, etc., all the way up to n. Okay, right. So this is the algebraic circuit. So the polynomial that we are finally interested in is computed in the top right gate of the circuit. Okay, and that's going to be the output gate of my algebraic circuit. Okay, so this is an algebraic circuit computing the elementary symmetric polynomial of degree D. Okay, and what's the size of this circuit? So again, the size is sort of like the number of wires. And you can see that every time I add a new layer to the circuit, I add something like, well, I calculated something like 4D wires. Okay, so every time I go from n-1 to n, I add something like 4D wires. And I do this something like n times. So I have something like 4ND wires, I think. So don't hold me to this. I may be not exact in my computations here, but it's something like order n times D. Okay, and since D is at most n, because we are looking at subsets of 1 to n, so there can be at most n of them. So the size of the circuit is order n squared. Okay, so this is a polynomial sized circuit for the elementary symmetric polynomial of degree D in n variables. Yeah. Any questions about this computation, this construction? Okay, great. So yeah, if not, so let me just quickly say that as an aside, this is not just an algebraic circuit, but it's also what is called a skew circuit. So if you look at the multiplication gates here, the multiplication gates, it turns out that if one of the inputs to a multiplication gate is always a variable. Okay, it's not a general input, but it's always a variable. And so, such a circuit is called a skew circuit. And it's actually a fact that every skew circuit actually also gives rise to an algebraic branching program. Okay. So this is just an aside, but this sort of nicely anticipates. Yes,
can I interrupt here?
Yes, please.
So since you said initially that product gates could have many wires coming into them.
Good. Yeah.
So then for a skew circuit, you would want that every product gate has at most one wire that is not a variable, right? Or
yeah, that's right. Yeah,
so in this example, all the product gates just have 2 wires. So one is a variable and
that's right. Yes. Yeah. Thanks very much for pointing that out, Meena. Yeah, you're absolutely right. Yeah, I should have said here, as for a skew circuit, every product gate has all but one of its inputs as a variable or a constant, and one of them is allowed to be something more complicated. Yeah. So that should really be the definition of skew circuit. So slightly wrong here. And it's a standard fact that every skew circuit actually gives rise to an algebraic branching program. And we won't see that in general, but let's see it for this particular family of polynomials. Okay. So in the next example, so I'm going to continue with this same family of polynomials, but what I want to now show you is that this actually has a family of efficient algebraic branching programs. Okay. So again, what's an efficient algebraic branching program? I want to be able to realize this polynomial as a projection of an instance of iterated matrix multiplication. Okay. And how do I do that? Well, again, I'm going to use the same recurrence, right? So I have this recurrence for E and D in terms of the elementary symmetric polynomials on lower number of variables. And again, it helps to not just look at E and D, but look at all the elementary symmetric polynomials of degree up to D. Okay, so I won't just look at this recurrence for degree D, but I'll also look at this recurrence for degree D minus 1, degree D minus 2, all the way down to degree 0, say, right? And I can write all those recurrences together nicely in matrix notation. And this is what it will look like. Okay, so if you write down these recurrences in matrix notation, I prefer to write it in terms of row vectors rather than column vectors. So if you do that, you're going to get something like this. Okay, so you can check that this is what it comes out to. But now you can see that you've nicely written one row vector in terms of an analogous row vector on n-1 variables. So you can repeat this recurrence. And if you keep going, you'll end up with this kind of decomposition for the family of elementary symmetric polynomials of degree up to D. Okay, so you end up with this decomposition. And now, since I'm only interested in E and D, I can easily get E and D by sort of just keeping the first column of the last matrix here. I can just keep the first column of the last matrix. And if I do that, I'll get exactly the first entry of the row vector, which corresponds to E and D. Okay. And in doing this, we have explicitly written down the polynomial E and D as a projection of a product of a bunch of matrices. Okay. And so you can see that, so what are the sizes of these matrices? The sizes of these matrices is exactly, they're all D by D matrices, right? So these are all, so let me write it here. Right. So these are all D by D matrices here. Okay. So this is, and since D is at most n, this is all a projection of IMM n n. Okay. So this gives you this polynomial, the elementary symmetric polynomial of degree D, as a projection of IMM n. Okay, so that gives you an algebraic branching program, and you can check that's an algebraic branching program, I guess, of size something like n squared or something like that. Okay, so this gives you an efficient algebraic branching program for the sequence of polynomials. Okay, and it's a small nice exercise here. So this is, we've written it as a projection of the iterated matrix multiplication polynomial, but we defined also algebraic branching programs in another way using directed acyclic graphs and so on. So it's a good exercise for those who are interested to sort of rewrite this construction, but using that definition. Okay, just actually write down the graph, write down the interconnections, write down the labels on the various edges. It's probably a good exercise. Okay. Does it make sense? Any questions about this? Okay, great. Yeah, so if not, so let me do a final construction. And this construction is a construction for formulas, for the same polynomial. Okay. And this is actually also a beautiful construction. So this construction is fairly non-trivial. It actually deserves kind of the title of theorem. So this is actually an idea of Benor from the 90s. So now I want to show to you that this elementary symmetric polynomial of degree D actually has a formula of polynomial size. In other words, it's in the complexity class VF. Okay. So how do I go about doing that? So recall that every polynomial, including this one, is of course a sum of monomials. And of course, that gives me some sort of formula for this polynomial. Unfortunately, however, this kind of formula has n choose D terms for the degree D elementary symmetric polynomial. And if I think of D as like n by 2, this is going to be exponential in n. So this is not very efficient at all. Okay. On the other hand, you can give a slightly more complicated kind of formula for this polynomial, which is much more efficient, which is of polynomial size. Okay, and that's the construction that we're going to look at. And this construction uses a very simple but a powerful idea that is useful in many other related situations. And this idea is that of interpolation. Okay, so what do I mean by interpolation? Well, it's just the standard fact that we know, right? So if you have a degree D polynomial, so in this figure that I've drawn here, the polynomial is like a quadratic. If you have a degree D polynomial, then you can determine the coefficients of the polynomial by evaluating it at D plus 1 distinct points. Okay, so I should have said here, I'm talking about a degree D univariate polynomial. If I have a degree D univariate polynomial, I can determine the coefficients of that univariate polynomial by evaluating the polynomial at d+1 distinct points and taking suitable linear combinations. Okay, so this is kind of a standard fact from linear algebra. It uses the fact that the van der Waals matrix is invertible, but this is something that's extremely useful in various places, and in particular, it's useful in this construction here. So how do we use that here? Yeah, so again, the idea in constructing the formula for E and D is to not look at E and D in isolation, but rather look at all elementary symmetric polynomials. Okay, so here we're not just going to look at elementary symmetric polynomials of degree at most D, but rather we're going to look at all elementary symmetric polynomials of degrees going from 0 to n. Okay, so there are n+1 of them. And we're going to look at them together as a generating function. Okay, so let's look at the following generating function, which is I sum over all j going from 0 to n. I have a new auxiliary variable that I call t. So I have t to the j times the jth elementary symmetric polynomial. Okay, so this is sort of a generating function for the family of elementary symmetric polynomials. And the nice observation is that this has a very simple form, which is just this. So it's just a product of 1 plus t times xi, right? And you can check this by just expanding. If you expand this out, the coefficient of t to the j will exactly be all those monomials in x1 to xn that multiply out exactly j of them. And that's exactly the elementary symmetric polynomial degree j. Okay, and let's call this a polynomial q of t. Okay, I'm suppressing the dependence on x1 to xn here. I want to think of it as a univariate polynomial in just t. Okay, and the interesting observation is that while the elementary symmetric polynomials individually look quite complicated and it's not clear how to write an efficient formula for them, this generating function actually is a formula of size order n, right? So this is just a small expression. It's just a product of n things. Each of them involves just a constant number of algebraic operations. So this is just a formula of size, a constant times n. So it's a very simple but powerful observation. And so the question is now how to use this observation in order to get a formula for the elementary symmetric polynomial of degree d, how to get a formula for each one of these tests. Yeah, and how to do that? Well, we're going to use interpolation. So if you're interested in the elementary symmetric polynomial of degree d, we're really interested in the coefficient of t to the d in this expression. And yeah, and now we have a polynomial of degree n. We're interested in the coefficient of some t to the d. It's a univariate polynomial q of t. And so what do? We just evaluate this polynomial at n+1 many points, take a suitable linear combination, and the coefficient will pop out. Okay, so we're going to take the polynomial q. This auxiliary variable t is going to get replaced by various scalars from the underlying field. So here I'll need the field to have at least n+1 distinct elements, otherwise this will not make sense. But let's assume that that's the case. So I evaluate this polynomial q at n+1 distinct points from the field. And by taking a suitable linear combination of them, I can get the coefficient of t par d, which will exactly be the elementary symmetric polynomial of degree d. Okay. So yeah, this is actually a pretty it's a beautiful and non-trivial construction. So any questions about this construction?
So here, this elementary symmetric polynomial is not scalar, so it is a polynomial in n variables.
Right.
Yeah. So interpolation works for ring also. Yeah.
Right. So yeah. Absolutely. So you can just, yeah, absolutely. The interpolation works definitely. So you can just, so one easy way of thinking about it is just assume that you're working in the field of fractions of, whatever ring you're working with.
Okay,
so
okay.
the ring is definitely a trivial domain. So you can work with the field of fractions and everything. Yeah, good.
Okay.
Yeah. Okay, great. So that's it. So this is the kind of expression you get. And you can check that this expression, so it's a sum of n terms, each of which have size n. So this is a formula of size just n squared. Okay, so you get a very simple formula. And in fact, it's a depth 3 formula. If you think about it, it's a depth 3 formula of size n squared for this sequence of polynomials. Okay, great. So, okay, great. So we saw a couple of nice examples. So now let's return to a little bit more abstract theory. So we defined these complexity classes. So when you have a family of polynomials, for example, like the elementary symmetric polynomials, we have VF, which is polynomials that have small formulas, VBP, polynomials that have small AVPs, and VP have polynomial size circuits. And what we saw was the elementary symmetric polynomials, for example, lie in all three of them. Okay. And in fact, this is not like a big coincidence, because it turns out that these three classes are nicely related. Okay, they in fact form a nice chain of inclusions. So VF is actually a subset of VBP. VBP is actually a subset of VP. Okay, and the fact that VF is a subset of VP is actually quite obvious, right? Because the way we defined algebraic formulas, they're kind of specializations of algebraic circuits, so it's kind of obvious. But it's slightly non-obvious to show that VF is a subset of VBP and VBP is a subset of VP. So both that are slightly non-obvious, and maybe I'll tell you a little bit about one of them. But all these inclusions happen to be true. So in fact, the third result I showed you implies the other two. Okay, and it's actually they're very interesting open questions as to whether these inclusions, either of them, are strict. Okay, so we don't know converse inclusions to either of them. We do know something, but we don't know whether these inclusions are strict or not. For all we know, they could be or not. So I guess this will be addressed in some of the future lectures on this topic. Okay, so I wanted to tell you a little bit about both of these inclusions, but I'm kind of slowly running short on time. So what I'm going to do is I'm going to skip the first one, which is actually a very simple combinatorial proof, and I'll tell you a little bit about the second one. Okay, so let me just skip this one. Let me tell you a little bit about why VBPs contain VP, and this is a fairly intuitive reason, right? So let's start with how we define VBP. VBP was defined to be the set of all polynomials that have small algebraic branching programs, or equivalently those that are nice projections of a small instance of iterated matrix multiplication. Okay, so it's natural that we first start with IMM and ask what kind of circuits does it have, right? And so now it's quite easy to convince yourself that IMM, let's say I'm multiplying n by n matrices, this has a circuit of size order n cubed. Okay, so it definitely has efficient circuits. Okay, so how do you see this? Well, it's just the standard matrix multiplication algorithm. Okay, so you just imagine that you're multiplying matrices iteratively one after another. What would you do? You do the standard multiplication operations, and if you do that, you get a circuit of this size. Okay, this is a kind of a nice exercise for you. It's kind of like the elementary symmetric polynomial, the first construction of circuits there, but it's a little bit more complicated, so it's worth working after. Okay, so what does this mean though? Well, what this means is that in general, if I have an ABP, right? If I have an algebraic branching program of size S on n variables, this immediately implies that this also has the polynomial represented by this ABP also has an algebraic circuit of size something like polynomial in S and N. Okay, and why is that? Well, it's very simple. We saw already that if you have an ABP of size S, then this polynomial is a projection of the iterated matrix multiplication polynomial with parameters S and S, right? So by the theorem above, this polynomial, the IMM polynomial, has a circuit of size S cubed, right? And now starting with the IMM polynomial, I can apply the projection and get a circuit for this polynomial PA, which is represented by the ABP. And so I can just make these linear substitutions. These linear substitutions will replace each variable in C prime by a linear combination of the variables of A, right? And that might increase the size by a factor of n or something, but that's not an appreciable increase. And so what we still get is a kind of a small size circuit for the polynomial represented by A. Okay. So in particular, if you start with a polynomial which has a polynomial sized ABP, right? So S is a polynomial in n. It's an ABP of polynomial in n size on n variables. Then you get a circuit of polynomial in n size. Okay. So if you start
S to the 4, shouldn't this be S to the 4? Because in every entry you're replacing, right? And there were S matrices. So blow up only.
No, so I'm replacing every variable in IMM-SS by a linear combination of n variables. Sorry, are you talking about the theorem on top?
No, the second, no, that is okay. The first one is corollary, you say is only S cube n.
Right, I guess I'm just replacing each of the underlying variables. So the IMM polynomial has a circuit of size n cubed. So I'm taking each of the kind of variable, the input gates of that circuit, and just replacing it by a linear combination of n variables. So that's going to blow up the size by a factor of n, but not more than that.
Correct.
Okay. All right. So that's it. So if you start off with an ABP of size polynomial in n, right? So if S is polynomial in N, this substitution is only going to keep it polynomial in N. So you also get a circuit of size polynomial in N. So what that means is that if a polynomial family has efficient ABPs, then it also has efficient circuits. In other words, we've shown that any polynomial sequence in VBP is contained in VP. Okay, so this kind of proves this inclusion. And it also illustrates an important fact, which I sort of brushed under the rug when I was talking about reduction sometime earlier, right? So for the proof on the last slide to work, it was important that we have polynomial sized ABPs to get polynomial sized circuits. In other words, you don't just want your polynomial to be a reduction of IMM, a projection of IMM. You want it to be a projection of IMM of not very large size, right? You want it to be a projection of IMM SS, where S is a polynomially bounded function of the number of variables, right? And this is natural when you think about reductions. You don't want when you're reducing from one problem to another, you want the reduction itself to be efficient. So if you have to compute M linear functions where M is a humongous function of N, that's not really an interesting reduction. So you want your reduction itself to be efficient so that you get an efficient algorithm over. Okay, so when we talk about projections, we really talk about P projections, where what we mean by P projections is that the number of variables in the target polynomial is bounded by a polynomial in the bounded as a polynomial function of N. Okay, so when you reduce one polynomial sequence to another, you want it to be the case that you reduce to a polynomially bounded instance of the target sequence. Okay, and what we really used on the previous slide was that if you have one polynomial sequence that reduces to another and the latter sequence has small circuits, so in the previous slide it was IMM that had small circuits, then the sequence Pn has small circuits as well. Okay, so what we really showed was that VP, what we really used was the fact that VP is closed under these kinds of projections. Okay, and it's not hard to show that in a similar way, VBP and VF are also closed under P projections. So these reductions or projections are a kind of a powerful way of reasoning about these complexity classes. Okay, great. So this point about reductions actually brings me to another important example, the example of the determinant. Okay, so we can also use projections to reason a little bit more about the determinant. Okay, so the determinant, as we saw, is an important computational problem. So where does it fit into all these complexity classes that we've seen already, right? So the first thing to note is that the determinant has small algebraic circuits. Okay, so the determinant is in the class VP. Okay, so why is that? So this is not an entirely obvious thing, but you can use the standard Gaussian elimination algorithm. Okay, but now do Gaussian elimination over your n by n matrix of variables. Okay, so you have a determinant of an n by n matrix that you're trying to compute. Now do Gaussian elimination on this matrix of variables, and this will give you a way of computing the determinant. Unfortunately, it also uses division. So it is kind of Gaussian elimination by definition uses division. So it gives you a way of computing a determinant via an algebraic circuit, but it's not really an algebraic circuit because you also have to divide things. Okay, so you also need gates which allow for divisions. Okay, so you can do that, but it turns out that when you have an algebraic circuit that uses divisions, you can always convert it to another algebraic circuit for the same polynomial that does not use divisions. Okay, and the new algebraic circuit is of size roughly the size of the original algebraic circuit, as long as the degree of the polynomial that you're computing is small. Okay, so this is kind of a very nice theorem of Strassen, kind of a good excuse to talk about it. So you start off with a circuit which has divisions, but you can convert it to a circuit that just uses additions and multiplications using this theorem. Okay, and there's this nice result of Strassen, and using that you can actually show the determinant is actually in BP. All right, so good. Okay, but that's not all. Right, so we have three complexity classes here: BP, BBP, VF. So why stop at BP? So, but it turns out that in fact determinant is not just in BP; it's also in VBP. Okay, you can actually put it so this is a slightly more involved argument, but the nice result of Berkowitz from back in the 80s that shows that the n by n determinant can actually be computed by polynomial in n-sized branching programs. Okay. And so what does this mean? Well, by definition, almost, by the definition of algebraic branching programs we gave, so this means that the determinant is a P projection of the iterated matrix multiplication polynomial, of the IMM polynomial. Okay, so a determinant is a p projection of the IMM polynomial. And not just that, it turns out that the converse of this is also true. Okay, so it's not just that the determinant is a p projection of IMM, the IMM itself is also a p projection of the determinant. Okay, so what this means is that the complexity class VBP that I defined as polynomials that are efficiently reducible to IMM could also have been defined slightly differently. It could have been defined in a similar way using the determinant polynomial instead. Okay, so every polynomial in VBP, it kind of reduces to IMM, but IMM itself is a p projection of the determinant. And so what it means is that every polynomial in VBP, polynomial sequence in VBP, is actually a p projection of the determinant. Okay, so we could have used this definition instead to define the same thing. And these two problems, determinant and IMM, are actually computationally more or less equivalent to each other. Okay, so this tool of projections, this kind of illustrates the power of this tool. These two polynomial sequences that are both very natural and important for us are kind of computationally equivalent to each other. Okay, and so this idea is actually a very important idea in this field of complexity theory in general, and particularly in algebraic complexity. And this is this idea of completeness. Yeah. So in general, when you have a class of polynomial sequences, so it could be something like VF or VP or VBP or whatever, we have notions of completeness for this class of computational problems. And we say that a given computational problem is complete for a class if it belongs to a class and every other problem in the class is efficiently reduces to this problem, right? So in this case, Pn, the polynomial sequence Pn is said to be C complete if this polynomial sequence belongs to C, and every polynomial sequence in C is a p projection of this polynomial sequence Pn. Okay, so what we just saw on the previous slide is that both the iterated matrix multiplication polynomial and the determinant polynomials are both VBP complete, which is to say that every polynomial sequence in this class reduces efficiently to these polynomial sequences, and these polynomial sequences are themselves in this class. Okay, and this allows us to make all sorts of interesting statements. So for instance, I told you about two complexity classes, VF and VBP. It's not known whether they're equal to each other or not, but they are equal because these two polynomials are VBP complete. You can say that they're equal if and only if the iterated matrix multiplication polynomial is in VF or the determinant polynomial is in VF. So if and only if IMM has small formulas or determinant has small formulas. Okay, so these are in some sense the hardest polynomials in this particular complexity class. And so in order to show that the entire complexity class is equal to VF, you just have to show that one of these two polynomials has small formulas. Okay, so is this reasonably clear? So, okay.
Yeah, Srikanth, I have one question.
Yes.
So when I think of the determinant, well, there are n squared variables that I'm really trying to look at, and it's a degree n polynomial in n squared variables. And now you're saying that it's the projection of IMM n, where the entries now. So can I always assume that those entries that I see there are just linear functions in these n squared variables that I'm really finally interested in? That's what it means, right?
Yes.
Or, huh?
Yeah, absolutely. That's
yeah.
Okay. Oh, I see. I kind of lost track of time here, so I guess I'm almost out of time. But let me now introduce sort of the
no problem.
main problem that I should have spoken about. Oh, sorry about this. Yeah. So let me sort of introduce the main problem that kind of motivates this area, right? The kind of main question, the VP versus VNP question, and this is sort of motivated by. Okay, so we have these computational problems. We have these computational models for solving them. So now what do we do when we are not able to find efficient algorithms for our given problem, right? So at some point of time, we would like to say that this computational problem, in fact, has no efficient algorithm. Okay, and this brings us to this kind of general question of proving lower bounds. Okay, and so the question that we try to answer here is: are there polynomials that do not have efficient algorithms? And these efficient algorithms can be formulas or algebraic branching programs or circuits or whatever. Okay, so are there polynomial sequences that do not have small formulas, ABP circuits? And you have to be a little careful in the way you ask this question. Okay, because if you ask it in a kind of in this setting, the answer turns out to be trivial. Yeah, and the reason is that the answer is yes. Yes, there are families of polynomials that do not have small formulas, ABP circuits, whatever. Yeah, and the reason for this is kind of very simple and in some sense even silly, right? And the way you prove this is just by a counting argument. So over a finite field, for instance, what you could do is that you could just count the number of formulas which are small, the number of ABPs that are small, or the number of circuits that are small, and you could give a bound on that. And on the other hand, you could count the number of polynomials that you might be interested in computing, and you just show that the number of polynomials is larger than the number of small formulas, and therefore there must be a polynomial that does not have a small formula. Okay, so you can make these kind of silly counting arguments. There are some variants of these counting arguments like dimension counting, etc., in infinite fields as well. So the answer to this question is actually yes. And in fact, there is a much nicer version of this even. So Rubesh and Yehuda, what they showed is that if you actually take there are, in fact, just by generalizations of these counting arguments, that there are polynomials whose coefficients are just zeros and ones, okay, such that any circuit for these polynomial, any algebraic circuit computing this polynomial is very large. And what does large mean? Essentially, this circuit is not much better than just simply writing out the polynomial as a sum of monomials. Okay, so if you're just, so the kind of the end result of this is the following, is that if you just want to ask the question of whether there exist polynomials that don't have efficient circuits, formulas, ABPs, whatever, the answer is yes. Okay, but so the question that we are asking, however, is slightly more nuanced than this. Okay, so the question that we are asking is not that whether there exist such hard polynomials, but rather are there explicit polynomials that do not have small formulas, ABPs, circuits. Okay, and what does explicit mean? And explicit in some sense means easy to describe polynomials. Okay, easy to describe. And the exact meaning of explicit is sort of subtle, and it can differ slightly based on application. But the most important meaning of explicit for us, the one that makes the most sense in our setting, is this notion of VNP. Okay, so what does VNP mean? So I'll give you kind of two definitions for this. So one is kind of an operational definition that you can use often, but it's not actually an equivalent definition. And then I'll give you the equivalent definition because the formal definition, because that's useful in certain situations. Okay, so here's an operational definition. So what is an explicit polynomial, right? So if I give you a polynomial, what does it mean for it to be explicit? Well, intuitively for us, a polynomial is defined by its coefficients, the coefficients of various monomials. So it's sufficient for a polynomial to be explicit that I be able to tell you what the coefficients of this polynomial are. Okay, so what does that mean? Well, the polynomial, let's say, is of degree at most d, and we know this degree parameter d beforehand. So there should be an efficient algorithm. Okay, now I mean a general algorithm here, not an algebraic circuit, a general algorithm, which when given the description of a monomial, right? So on the left of this box here is just a sequence of exponents that describe a monomial of degree at most d. So when given the description of a monomial, it sort of spits out, computes the coefficient of this monomial in this polynomial. Okay, so for an example to keep in mind is something like the determinant, right? So the determinant I know is a polynomial of degree n in n squared variables, right? But it's the coefficients of the determinant are very nicely described, right? If I give you a monomial, a candidate monomial of degree at most n, I can easily tell you what the coefficient of this monomial in the determinant is. I know that if it has a certain form, unless it has a certain form, the coefficient is 0. And if it has a certain form, then the coefficient of that monomial is the sign of some permutation. Yeah, and this is something that's easy to compute. Yeah, and this is sort of a defining feature. It's not a defining feature, but it's something that's sufficient to conclude that a polynomial is in VNP. Okay, and this is what I call like an operational definition, in the sense that most times when you want to show that a polynomial is a VNP, you can use this definition and kind of conclude that a polynomial is a VNP. Right? But this is not the formal definition. And the reason this is not the formal definition is that from here, it doesn't follow that if a polynomial has a small circuit, then it's in VNP. Okay, if I just tell you that a polynomial has a small circuit and I give you a circuit for it, it's not so clear that I can compute the coefficients of various monomials in that circuit very efficiently. So it does not follow that the polynomial is in VNP. And definitely that's also something we would like. We would like that anything that has a small circuit is also explicit. Okay, so in order to kind of make both of these requirements come together, we have to look at the formal definition a little bit. So let me just flash that formal definition and soon conclude. Okay, so a polynomial sequence is said to be in VNP. Okay, if there's a polynomial sequence in VP, so there's a different polynomial sequence in VP, such that the sequence Pn sort of can be written in terms of Qm in some way. Okay, and what is that way? So it turns out that so the way Pn will be written in terms of Qm is that every polynomial Pn can be written as some polynomial in this Qm sequence. But now I just don't take the polynomials in Qm, but I sum over some of the variables. Okay, so let me just say that again. So I take, maybe suppose I want to represent the polynomial Pn. I take the n plus rth variable, n plus rth polynomial in the sequence Qm. And now I treat the last r variables in this polynomial Qm as auxiliary variables. Okay, and what I do is I sum over all Boolean values to these auxiliary variables. Okay, so I take y1 to yr, these are the auxiliary variables. I sum over all Boolean values to y1 to yr. And as I do that, I get a polynomial in just the first n variables, which I think of as a polynomial x1 to xn, and that should be the polynomial Pn. Okay, so you can think of this as kind of analogous to a reduction, right? Because you're using a polynomial, another family of polynomials to compute the first family, but it's by no means an efficient reduction, because this sum is running over an exponential in r many quantities. So that's a very large number, and we allow this parameter r to be a polynomial in n. Okay, so the polynomial sequence Pn can be written as an exponential sum over kind of instantiations of the polynomial sequence Qn. Okay, so it's kind of a complicated definition to digest. So it's not an operational definition by any means, but in particular, it gives us that Vp is contained in Vn. Okay, because now in particular, if I want to show that a polynomial sequence that's already in Vp is in Vnp, then I can just take Qm to be equal to Pn, and I don't have to sum at all, and this will give me what I want. Okay, so in particular, Vp is contained in Vnp. Okay, so if you want to get your hands on this definition, I think the best way to do it is to kind of prove by hand that some polynomial, let's say the permanent polynomial, okay, that we saw some time ago, is in Vnp using this definition. Okay, and it's kind of a nice exercise. I've given a little bit of a hint here, so let me not get into that. But let me just kind of conclude with my final slide. Okay, so the kind of defining question of this area, the one that we're interested in, the question of lower bounds, therefore, is about proving explicit lower bounds. Okay, so we want to prove a lower bound for an explicit polynomial. And for us, an explicit polynomial is a polynomial in Vnp. Okay, and the question we are trying to answer is every polynomial in Vnp, does it also have an efficient algebraic circuit? Okay, does it have an efficient algebraic circuit? And the conjectural answer is no. Okay, so this is called variance hypothesis. Variance hypothesis is that Vp is not equal to Vnp. So there are family polynomials in Vnp that do not have efficient algebraic circuits. And that's what we'd like to prove. Okay, and Valiant, when he started studying this question, actually also proved a bunch of other results about this. And in particular, he showed that just like IMM, I said some time back, IMM and determinant are complete for the complexity class BBP. He also showed that Vnp has a hardest computational problem inside it, and that's just the permanent. Okay, so the permanent is Vnp complete. So which means that Valiant's hypothesis sort of reduces to asking whether the permanent has efficient algebraic circuits or not. Okay, so if you kind of want to know why we are always thinking about the permanent versus determinant, etc., it's because the permanent is Vnp complete. So permanent is sort of the hardest problem in this very large collection of explicit polynomial problems, and it happens to be Vnp complete, and it has algebraic polynomial size algebraic circuits if and only if all the problems in Vnp have efficient algebraic circuits. Okay, so that's about Vp versus Vnp. But if you recall, we introduced a sequence of complexity classes. We also spoke about Vf and Vbp. So what about Vnp versus Vbp? Maybe we're not able to answer Vnp versus Vp. What about Vnp versus Vbp? Well, again, here, Vnp equals Vbp if and only if the hardest problem, permanent, is in Vbp, right? And as we saw some time ago, every problem in Vbp is a projection of a small, every problem in Vbp is an efficient projection of a determinant or IMM, right? So this problem is exactly the problem of whether the permanent is a projection of a small determinant or a small instance of IMM. Okay, so if you've been following some of the earlier lectures in the series, then you've seen that there's been a lot of thing about how we show that permanent is in how do we show that the permanent is not a projection of a small determinant or IMM? And this is exactly why we look at these questions, right? Because that's exactly equivalent to VNP versus VBP. So it's not exactly equivalent to VP versus VNP, but it's exactly equivalent to VNP versus VBP. Okay. And in fact, proving strong enough results in this direction will actually be able to, you'll be able to actually prove VP not equal to VNP as well. But let me sort of skip that. Okay. So let me just conclude with a final remark, which is that from a computational point of view, the reason the VP versus VNP question is so interesting is that it seems like a more tractable version of another question in complexity theory, which is called the P versus NP question. Okay, and the P versus NP question is a similar question in the in spirit to VP versus VNP, where we are not just talking about polynomial problems, but more general computational problems. And again, there we would like to be able to prove lower bounds, but we are seem to be very, very far from doing that. But VP versus VNP can be shown to be a formally easier version of this question, in the sense that if we are able to resolve the P versus NP question, then in particular, we would be able to resolve the VP versus VNP question as well. So in particular, proving VP not equal to VNP is seen as a stepping stone to this other question. Okay, so I think that's all I have time for. So let me stop here. And yeah, sorry for going over time.
Yeah, so Pascal Coiron has a comment, maybe mention, that he's posted for everyone. Okay, and so are there any questions for Srikanth? A lot of questions during the talk, so there's a clap. Yeah. So any questions? No, no. We've had a lot of good questions actually already. Maybe that's why. Yeah. So if there is, so Srikanth, just send me and Thomas your slides, please, later. Yeah. Oh, sorry. Let me stop the recording. Yeah.